So errors. Errors are something that come from any measurement that we make, and they describe the uncertainty in which we make a measurement. So if I was to measure, say, use a ruler, and I was to measure the length of something, you know that I can only measure it to the accuracy that the ruler has lines on it, and then basically I have to guess which line it's closest to. Well, I can usually see which line it's closest to, and this state basically describes the uncertainty in which we make a measurement. So just like a number is useless without its units, a number is also useless without its error in chemistry, and I'm talking about. So whenever you talk about numbers, you've always got to include the error associated with them, and also the units. So let's have a look at how we use them. How do we use errors? How do we calculate errors? Now let's just say let's give an example. This might make it a bit easier. So let's say I've got a conical flask here. Let's see how well I can draw this. Oh, that's better than before. Alright, so it says that it is a 20 ml flask, and we're asked to make a solution up of concentration 50 grams per litre, and we can weigh out the let's just say it's a tablet. We're trying to make up a solution of a tablet that's 50 grams per litre. Right, so let's think about what skills we have to use in order to work out the concentration, the actual concentration from a tablet. So there's two things we need to know. We need to know how errors add and subtract, and secondly we have to know how errors multiply and divide. So if I want to add or subtract errors, then I can use the absolute errors. So let's say I've got two numbers. I'm adding and subtracting them, which means that they're in the same dimensions. And what we use is Pythagoras' theorem, and to work out the root mean square, that's what it's called. And so I like to think of this visually. If I've got, let's just say I've got this error B and I've got this error A, what I'm trying to work out is this length here, which is C. That there is the root mean square of the error. And we know from Pythagoras' theorem that a squared plus b squared is equal to c squared. In order to get rid of this square for the c, we can square root both sides, and that cancels out the square for the c, and we're left with c is equal to the square root of a squared plus b squared. Now the cool thing about exponents is that they make things that look scary not so scary. So what do you think a square root is? Well, quite simply, it's just this to the power of a half. So I mean, it's very simple. So this is how we work out the error. Now the problem comes when we want to multiply and divide. Now the reason is that the units or the dimensions are not the same. And that makes sense. You know, if we're looking at concentration over here, we're going to have to divide some mass by a volume, and they're completely different units. So it doesn't make sense to use their absolute errors, or the errors that we'd find on the end of those two numbers. So what we do is we find the percentage error, and we apply Pythagoras' theorem to work out what the root mean square of that error is. So in order to find the percentage error, what we have to do is we usually put it into a fraction. We then convert it into a decimal, usually on our calculator, and then we shove it into a percentage. Oh, sorry, it's going very slowly. Alright, so let's just say I've got 0.1, that's my error, plus or minus, and that is out of my 3. And so the fraction can also be written as 1 out of 30. The decimal is going to be I think it's 0.1. Give me a second. Oh yeah, that was close. Recurring, that's what that dot means. And if we were to convert this to a percentage, we times it by 100. And that's because percentages are out of 100, so it's kind of like another fraction. And so we'd get 3.3%. So let's just say this is our percentage A. So if we were to use Pythagoras' theorem, we'd go A squared plus the second percentage error squared, and then this would all be square rooted, which is to the power of a half. So that's nice and easy. So now let's go about doing this calculation. So now that we've got all those skills, so let's say we weigh out, so what we want to find out firstly is roughly how much to weigh out to give us this concentration. So we know the formula from the units. C is equal to grams, which is mass, divided by litres, which is volumes. If I want to give myself mass on the right hand side here, I times both sides by the volume, and you'll see that these two cancel. This is what algebra is all about, you timesing both sides by the same amount and cancelling. So we're left with mass is equal to C times V. So roughly, if we times 50 by 20 mils, we'll get the but remember that it's mils, so we have to change that because it's scientific notation. So we've got 50, we want 50 grams per litre times 20 mils, and you'll see that currently litres and mils won't cancel because they're different units because of the scientific notation. So what we have to do is times it by the conversion factor, and in this case we know that in let's say a litre is equal to 1,000 mils. So we want to cancel mils, so we just times it by this. So litres 1,000 mils. You'll notice that the mils and the mils now cancel, and the litres now cancel, and we're left with mass, which is very handy. So 50 times 20 is going to give us 1,000, and that's going to be divided by 1,000, our conversion factor, and that's just going to give us 1. So we need roughly about a gram in order to make up this 50 grams per litre. So let's say I measure it out and I get 0. Well, I'll make it better because we have to deal with absolute errors. So let's say I put the watch glass on the weighing on the scales, and I zero the watch glass to 0. So I add in 0. Sure everything's right. So I zero the scales to the watch glass, and then I'm going to put in 1 gram. But let's say it goes a bit over, so it's 0.002. And I know that the numbers that are fluctuating are all the way down here, and so I know the error is about 0.0, let's say 1 gram. And actually the scales in the lab can even go smaller than this. Can have even a lower error, which is pretty remarkable. And this is why we love using the scales in order to put a certain mass into a volumetric flask, because the errors are so incredibly small that the main error ends up being the volumetric flask itself and how accurately we can measure out 20 mils. So the next thing we're going to do is we're going to empty the watch glass into the volumetric flask, and there we go, and we're going to re-measure the scales, and when we re-measure the scales we get 0.1 plus or minus 0.001 grams. Alright, so now we have to subtract these two numbers here. This is the with the tablet, and this is after. And so we have to subtract these two numbers, so 0.002 plus or minus 0.0001 grams minus 1. Oh, sorry. Let's say we remeasure it and it's 0.01. Sorry for that being a bit confusing. Alright, so when we subtract these two, we can see that what we're left with as the number is 1.001 grams. Now how do we deal with the errors? Now because we're subtracting, we can use the absolute errors. So we can use these errors here, we don't need to convert them to percentages, which is really nice and easy. So, so basically, have I got an extra 0 in there? Yeah, I do. Oh, that was going to be bad. Alright, I'll just remove one of these zeros here. Okay, that's better. 0.1. So we can just take the root mean square of that, and you'll actually find that it's 0.001. So it's really easy if the error is the same, and that's why I chose them like that. But it's reasonably easy to calculate that. So now that we've got this here, which is our mass, we have to put water into this volumetric flask, fill it up to when the bottom of the meniscus is on the line, and then we actually have our solution. And so And so we want to know not just a rough concentration, because this means nothing to us in physical chemistry. We want to know precisely what the concentration is so that we can use it as, say, a standard, or we can use it to measure the concentration of another sample. So we look at the flask and we say, what is the error associated with that flask, and we look up in our table and we get that 0.02 mils. Let's just say it's that just makes it a little easier. And we know from up here that the equation is C equals M over V, and so if we're going to calculate this, we go the mass, which is 1.001 plus or minus 0.001 grams, divided by 20 plus or minus 0.02 mils. Alright, so that's fairly straightforward. So the next thing we have to do is we have to work out the fractions. So if we go 0.001 divided by 1.001, that gives us 0.0009. And this is our decimal. We have to convert it to a percentage. We times it by 100, move the decimal point 2 places, and we see that we're dealing with, an error of 0.1% if we were to round. So very, very, very small error. And this is why measuring things out is so good. So the second thing we have to do is work out the error for the percentage error for the flask. So I'll just calculate that, and we get 0.001. Times that by 100, and we get roughly the same, 0.1%. And so we can divide these two numbers, and then we can find the root mean square, which is actually going to be also 0.01%. Now, once we've got the final concentration, which is 1.001 divided by 20, so this here is the number of grams per mils. Convert that to liters, we times by 1,000, because that's the conversion factor. Sorry for that. And so we get that it's basically 50.05 grams per mil. Now, what's the error? The error is going to be 0.1% of this number here. So in order to work that out, what you do is you have to convert this back into a decimal. So it's going to be 0.001, and you times this decimal by the number that we've just calculated, 50.05, and I'm going to times that by 0.001, and that gives me an error of 0.05. And so it basically is 50.05 plus or minus 0.05. 5. And actually it's 0.05005, but because our number is its last decimal places, there's two decimal places back, we just round that to the nearest digit in the error. So there you go. This is now our concentration, our grams per litre, and this is how we can now calculate the concentration of other things and make up standards. So hopefully this has been helpful. This is really how you use it. When you're adding and subtracting, you can use absolute errors, and you use Pythagoras' theorem to find what's called the root mean square, or the RMS value. If you want to multiply and divide, the units and the dimensions are not the same, so you have to work out the percentage error. And once you finish working out the percentage error, you work out that percentage of the final answer, and that's how you get your final value. So that took longer than expected, but hopefully that example is helpful.